Welcome back to my channel. This is part 10 of our Introduction to Calculus series, and today we're exploring integration rules. Let's get started. In this video, we'll talk about integration rules and techniques, starting with the basic ones. As you're noticing, they're very similar to the rules for derivatives, so I won't go into detail. Now let's take a quick look at a few rules unique to definite integral. Swapping the interval changes the sign of the result. If the start and end of the interval are the same, the area is 0. You can split the integral over subintervals. Consider the following integral. Notice something interesting? If we treat the argument of the cosine as a function gx, then the integral is multiplied by the derivative of that function. Let's replace gx with a new variable u. Then du is the derivative of gx, which is 2x dx. And now, we can compute the integral easily. Finally, we substitute u back as x squared. This technique is called integration by substitution. Let's make our integral a bit more challenging. In this case, we're not multiplying by the exact derivative, but it's still there. We just need to use the same technique. So let u be the argument, and du be its derivative. However, the integral has 2x instead of 6x, so we have to adjust. Use it in the integral. Now we can solve it, and replace u to get the final result. Let's look at this integral. Here, we cannot use substitution, because the cosine is not multiplied by the derivative of its argument. Instead, we need to apply another technique called integration by parts. This technique is based on the product rule for derivatives, which we covered in the video on differentiation rules. Now, let's take that rule and integrate both sides. The integral of a derivative simplifies to the original function, so we're left with the product of the two functions. By rearranging the equation, we obtain the formula for integration by parts, which can be rewritten using differential notation. Now that we know the formula, let's solve our integral using this technique. The first term will be u and the second will be dv. The derivative of x squared is 2x. The antiderivative of cosine is sine. We substitute into the formula and simplify. Notice the new integral. Once again, we can't use substitution because the derivative of the sine's argument isn't x. So we apply integration by parts again. Once again, we choose u as the first term and dv as the second one. The derivative of x is 1. The antiderivative of sine is negative cosine. We substitute into the formula and simplify it. And now we have a simpler integral, which is sine of x. We simplify the equation and get the final result. Don't forget the constant c. It's very important to choose u and dv wisely when using integration by parts. Let's look at this example. First, suppose we choose the first term as u and second as dv. The derivative u is the function ex. The antiderivative of dv is x squared over 2, because its derivative is x. Substitute into the formula. Notice that the new integral now involves x squared, which is more complicated than the original. So this choice made the problem harder. Now, let's choose the opposite. The derivative of u is 1. The antiderivative of v is ex. When we apply the integration by parts formula, we end up with a much simpler integral, which makes the problem significantly easier to solve. But how do we choose correctly? For that, we use the Lyate heuristic, which stands for logarithmic, inverse trigonometric, algebraic, trigonometric, exponential. This rule tells us which function to choose as u. Pick the one that appears first in this list. Let's use it to solve our final integral, which is a definite integral. Ignore the limits for now. We'll return to them later. Notice that the integrand combines a trigonometric function and an exponential function. According to the Lyot rule, the trigonometric function comes first, so we choose u as sine x and dv as e raised to x. The derivative of u is the cosine, and the antiderivative of dv is still the exponential function. Applying the integration by parts formula, we get a new integral that again involves the same types of functions. This time, we set u as cosine and dv as e raised to x. So, du is sine negative and v the function e. Substitute again and simplify. Notice that the original integral reappears, the one we want to solve. Let's call this integral I. Now we have an equation which we can solve for I. Move I to the left side, simplify, and find its value. Finally, we apply the limits using this standard notation. Calculate the upper limit, then the lower limit, subtract the two results, and obtain the final value of the integral. And that concludes our lesson. If you've learned something new today, make sure to like the video and subscribe. I'll see you in the next video.